Okay, so welcome back, and this is where we stopped in the last lecture, right? So we were discussing about a very interesting model, which is something like this, right? This is sort of a very comprehensive model where the image is degraded by some function, right? And this function example we already discussed, something like it can be blurring, it can be motion artifact, something like motion blurring, for example, or it can be something within the sensor itself, some sort of let's say out of focus effect and all those things. So it is treated as a convolution operation where h of xy will get convolved with f of xy. So the resultant of that is something like which is a corrupted or degraded image, right? And then to that there are a lot of noise that we discussed, types of noise that we discussed, all the way going from Gaussian to the salt and pepper type. And then you have g of xy. So our objective as an image processing engineer is to actually work on this g of xy and try to come as much close to f of xy as possible, right? And then for that purpose our objective is to come up with a restoration filter, okay, some sort of a filter which can actually nullify the effect of noise and deconvolve the effect of this degradation function, and that's what f hat of xy. So all in all, our aim is actually to make f of xy as similar to f of xy. I mean, if you can make it exactly equal, that's like nothing, but that's not possible all the time. So try to make this guy as close to the f of xy as possible, right? So that's the objective. Okay, so again the noise model, this part is all common, and you're already aware of all these aspects, so I don't want to discuss it again. So this is the generic expression. So f of xy convolved with the degrading function added with the noise, right? And you get g of xy. Okay, in the Fourier transform domain, this convolution becomes multiplication, so it's a much simpler model. So the Fourier transform of the corrupted image is Fourier transform of your original image multiplied with the Fourier transform of the degrading function added with the noise, which can be as simple as white Gaussian noise. Okay, so our objective is to recover that f of uv. Okay, and if we can do that, that's great. So what are the challenges, right? We need to maybe noise, this part is maybe easier, as we discussed. It's you can come up with some sort of a filter, something like smoothing or median or whatever, and may be able to remove the noise. But the estimation of this guy, okay, h of xy, or we call h hat because that is an estimate. We can't exactly reproduce that blurring function or motion blur most of the time, so we can only estimate that. If we can do that, then probably we can able to get back the original signal or original image as close as possible. Okay, so that's one important challenge. Okay, so how shall I go about it? Some example, let's discuss about some examples, some specific examples where we are able to recover that h of uv, the corrupting function, the degrading function. Okay, so one way to go about experimentation, this typically a lot of people do, and if you go out and work in industry, you may have to do this many times, is to get that impulse response. For example, if your camera has a blurring effect, you have to find the transfer function for that blurring effect, right? So how shall I go about it? Try to find the impulse response of your sensing system, the camera sensor. So for example, you can do something like you create an artificial source which is something like dark everywhere, and you have a bright focused light coming out of it. So this is like you're creating an impulse in front of you, right? And you're trying to capture that. So the resulting image will ideally has basically, you know, the input and the impulse response you rightly, I mean, sort of captured in that sense, right? If you try to take the picture of this particular scene, essentially what the image is, the impulse response of your sensor or transfer function, right? So that is one way to go about it. Or you have to estimate. Okay, so you take a portion of the image. This I will show you with an example during the hands-on. So in many cases, what people say that within the image itself we have that transfer function hidden somewhere. Okay, so this is very common in let's say you take the image of the space. Okay, so you want to actually take the image of moon, and along with the moon you will have images of the stars, right? And all these stars can be treated as impulses, right? Because they are so small in the entire space. Everything is dark and you find a star. So if you have the image of a star captured, that is equivalent to something like the transfer function of your camera. So what you need to do is you use that as the degrading function and try to see whether you can improve the image of the moon, okay, for example. So that's one way to go about it. You focus on the star, you may get the de-blurred image, blurred image of the moon. Then you use that transfer function to come up with a de-blurred or deconvolved high resolution image of your moon, okay. So I'll explain that in more detail when we have the hands-on session. So we have a specific example going in that direction. Okay, so there are several ways. So estimating the degrading function is definitely a challenge. In some cases you can do some experiments to capture that. In other cases within the image also, maybe locally you may be able to get that, okay. So moment you get h of u, we will see what are the approaches that we can do to recover the original image back. So okay, f of x by back from g of xy. Okay, so one simple straightforward way, as you can obviously think of, is sort of a plain division, right? You assume the noise, let's assume from now onwards for a moment that noise is minimal, there is no noise. So you have g of uv is equal to f of uv, h of uv, right? And then in that case f of uv ideally is g of uv by h of uv, right? And that's what exactly is expressed here, right? So quite straightforward, right? I mean, this is the easiest you can think of, division in frequency domain, right? But it typically is usually bad because in some cases it enhances the noise, because our assumption was like noise is minimal, right? So you expand this, g of uv is nothing but f of uv multiplied by the degrading function added with the noise. If you divide that by h of uv, this guy will go definitely f of uv, but there is a noise correction, or this is dangerous sometimes, because what happens is this factor will go extremely high, and instead of having a better image you get a worse image than your original observed image, okay. So you will get a worse image than g of uv, okay. So you have to be careful. So I'll show some results in that direction as well. So most of the time a simple inversion or a simple division is really not possible, okay. So the concept was, in this case, is like the degrading function, so this guy will be nothing but 1 over h, right? It will work in many ideal scenarios, but in practical scenarios this is going to fail. Many problems are there, the noise get amplified. Even otherwise also, if there is a zero value here, imagine h of uv is having a zero value, it will really boost the 1 by 0 is infinity, right? So it will just boost the image, the artifact like hell, okay. And one way to solve that is you add a small epsilon here, right? Some small factor here to overcome that problem. But even if you do that, this factor is a problem. And I want to actually illustrate this part using a figure here. So don't look into all these, just maybe I'll use the zoom tool so that it becomes clear to you. So let's take this part, okay. So you have the original signal. So I'm not showing image, but a signal here which is easier to interpret for you. So this is a Fourier transform of your original signal, the ground truth, okay. So this is something like this, okay. Something like a low pass, right? You have significantly high low component and very low high component. So it's like a low pass signal, okay. So low frequency signal, okay. And then there is a degrading function which is also similar to a low pass, but then you have to multiply these two, okay. So the result is something like this dark signal which is shown over here. The original f of uv is this, and it is degraded to look like this dark signal, okay. So just look at this, and now we are going to add some noise, additive white Gaussian noise. That's why it's flat, all frequencies are sort of equally contributed. You add to this, you get something like this. So you have to think of this is something like this part will get added, so the black will again shift up in this region, okay. And then this guy will be actually adding on top of this. So it may look like, I'm just trying to draw, let's actually see that, okay. Let me just go back and see this thing. So I'm just trying to see, it may look like this guy slightly shifted up because you're going to add noise, okay. So it will look like something like this, right? Because below this noise will get impacted. So this will be the observed signal for you, okay, which is actually corrupted by this guy and added with this noise. It looks like this red signal, for example. Now what we are going to do in the case of an inverse operation is actually, okay, let me again zoom, okay, so invert this guy, okay, so the invert of this guy is basically this guy. Now if I do an invert operation, you basically multiply by this component on this guy, right? So that's what you're going to do. So basically you do this multiplication, and then what essentially happens is you may get something like this red instead of the original signal, which is blue, because you can obviously see that because this portion is less weighted. So obviously this will go like this, and then this is amplified, so this noise is really going to get amplified, and that's what you're going to get. So the original signal was this nice blue curve, but the recovered signal will be something like this, and that means you're really going worse from even the observed signal. Observed signal was, I was showing you the red signal here, right? That was much better than this red signal which is over here. I hope I'm not confusing you. So the major problem here is, again let me just reiterate entire stuff, okay, so that it will be easier for you. So the observed signal, let's ignore all these u and b because it's just a coordinate representation, right? So let's put this way. So my observed signal in Fourier transform, G is equal to my original image multiplied by the degrading function h and added with some noise n. Now I am going to do an inverse filter on this, okay. So then it as simple as that, you multiply everything. So 1 by h is multiplied by G. If you do that, h and h get cancelled, so f plus n by h, okay. So this factor is sometimes going to screw you, just like shown over here. So this is important, you have to be careful, and that means a simple inverse filtering, even though it looks very elegant, it's completely useless in most of the practical scenarios, okay. So let's see what are the other options now available, and that's where one of the most common filter, which is commonly known as Wiener filter, is heavily used in signal as well as image processing, okay. So this is heavily used even now in the era of neural networks. Still Wiener filters are used, and this filter is a filter which is optimum in the mean square error sense, okay. So what essentially what I'm talking is simply as simple as this. So let's say your recovered signal or the restored signal is, or image is f hat of xy. So if you have recovered the origin, if you have recovered the image using Wiener filter, it is optimum in this sense, okay. So the mean square error, so basically you square the error, so error between the restored image and the original image is squared, the error is squared, and then you mean it up, okay. So basically x, y, and then you mean it up in terms of let's say m rows and n columns. So this is your mean square error, okay. So if you have used the w, okay, or the h, so instead of 1 by h, I'm going to use a new filter which is w, okay. So let me make it very clear, okay. So G is your observed signal, so you're going to actually multiply that with w, everything in Fourier domain, of course, in this case. So if f hat is what you observe, this f hat will have a minimum square error with respect to f. So that is the meaning of it. So if this filter, this w is Wiener filter, you are going to get an optimum filter in terms of mean square error between the original image and your restored image. At least theoretically, it's possible to prove, okay. So what exactly I mean is this, okay. So what are the advantages of Wiener filter? It incorporates, it's in a way, when you do a mean square error between the restored signal and your original image, of course you don't know the original image, so that is a beauty, it will come later, so we will understand, because you don't know the ground truth, right? You only have the degraded image with you, so and then you want to restore that to a very good image. So okay, so the how shall I go about it? It's a beauty about it, so we'll discuss that soon, okay. So the important point to notice here is Wiener filter in a way incorporates both the degrading function effect and the noise effect, okay. So you don't need to treat them as separate problem anymore, you can treat it as a single problem, and the objective is actually to come up with a minimum square error, okay. First we will see empirically, assuming that we know the f of xy or capital F, which is the Fourier transform of f of xy, assuming that we know that, okay, let's theoretically derive what is that filter looks like, and then you apply that filter on the degraded image. You will get an image, a restored image, which definitely is theoretically optimum in the sense of mean square error with respect to the ground truth. Okay, so that's the beauty about this filter. Okay, so the underlying assumption, yeah, this is very important. So I said it incorporates the degrading function as well as the statistics of the noise, but the underlying assumption is that the noise and the image are uncorrelated. If there is a noise which is actually correlated with the image, then it's very difficult. This won't work actually, it fails. The hypothesis is that the noise which is present in the image is not correlated with the image, which is more or less true, right? Because you can think of something like one pixel to the other pixel, the noise is random. Okay, so it's if it is related, that means it's part of the image. Right? It's very difficult to actually recover or improve the image further. Okay, so it's very difficult. So it's very important to have this assumption in mind. And now, as I said, Wiener filter, the objective is actually to minimize the mean square error between the ground truth and the restored image. So you're going to restore the image, it looks like f hat of xy. You try to minimize the error in terms of its mean square error. Okay, and in the Fourier transform it looks like this. Okay, so those who studied digital signal processing can easily understand that the mean square error in time is same from Parseval's theorem. It is equivalent to reducing the spectrum difference. Actually, the Fourier transform of original signal minus the Fourier transform of the estimated or the restored signal or image, you have to minimize this. Okay, and if you expand this guy, you already know that it goes to this particular thing, right? And then this is basically your G, right? This is your G, and then you have a filter which is going to actually multiply. Okay, always remember that block diagram. Okay, so you have, I mean, let me just spend that time. This is F. Okay, so this is H, the degrading function. Then you are adding noise to it, right? So some sort of eta, and then basically you have the observed signal which is G, and then you are going to pass it through a filter W, and this is your F hat. Okay, so in terms of Fourier transform, this is F which is multiplied by H added with noise N. Okay, so this will form your G. Okay, and then your G is you again multiplied by W, and that will form your F hat. So that's what exactly I'm writing here. So there's no confusion, I hope there. Okay, and then the mean square error of that. So basically this is unknown signal which you don't know, unknown signal or image, the corrupted signal, corrupted by the blurring function, for example, plus the noise. So that's there, and then this is the Wiener filter for us. Okay, so this is an expanded form. So our objective is actually to minimize this error. Okay, and let's do that derivation. So all the details are available even in the Wikipedia page, for example. So it's a very simple, quite straightforward derivation. And again, I'm going to remove that u and v terms so that expressions can be written very simply. Okay, so this is exact reproduction of what we had in the previous slide. Okay, there's nothing extra here. Okay, so your objective is to minimize the error between your original image, which is an unknown image, by the way, but this is a theoretical estimation that we are trying to do, theoretical proof that we are trying to do. What is that value of W is what our objective is. Okay, so objective is to find that Wiener filter coefficient W. Okay, so what sort of kernel shall I use, what sort of filter shall I use? So objective is, don't get lost actually, objective is to find this W, and my assumption is that, or my aim is that what is objective function, I want to actually find the values of W which minimizes this error. Minimizes what? Error between my ground truth, which is F, and the corrupted, I mean the recovered signal, right, which is G multiplied with W. Okay, so always think that way. This entire factor is your observed signal G. You are going to filter it using W, which is in Fourier transform, it is nothing but multiplication, and then you find the error between those two. Okay, so let me just make it simple for you if you are confused. So F is your original, and GW is your recovered signal, right? That is your F hat. Right, you are basically finding the square, this is error, and square of that, and then you basically sum, which means the mean of it, right? So you are going to reduce that minimum square error, you want to minimize that, that's your objective. Okay, so if I expand this, okay, if I put W inside or if I expand this like F minus FH W plus NW, and if I put F outside, I will get something like this. So f of 1 minus hw minus nw is simple direct substitution, right? And then this is nearly equal to, okay, so this is nearly equal to, see this, okay, nearly equal to, if I expand these two, it's sort of nearly equal, not exactly equal, it's nearly equal to this function, okay, f square plus this square plus n square plus w square. And now our objective is to minimize this error, okay. So this is as simple as that. You differentiate this with respect to w because I want to find that minimum value of, or I want to find that w which minimizes this error, right? That's my objective. So it's now straightforward differentiation, okay. If you do that partial derivative with respect to w, you end up in getting this. So basically you have the derivative of this and you equate it to 0, okay, derivative of this with respect to w and equate it to 0, you get this function on the top, okay, this particular function, and then you do some rearrangement, okay. By the way, this complex conjugate and all these are quite straightforward. It's coming from your complex algebra, okay. And then if you put w on one side, you get an expression which is something like this, okay. And you can further simplify this. So this is quite straightforward. I will share the slide so you can go through, and if you have any question, we can always discuss. There's no issue there, okay. And now what I did from here to here is basically I divided by f square, right? So this term and this term will go, and this guy will come, and there's a beauty about this term, we'll come to that, okay. So you have h transpose at the top, okay. So maybe I'll spend some time here. So this h square, right? So h square, what we did actually here is this f term will go from all, and this part is come, right? And then yeah, this part actually is taken out, okay. So this h, if I take 1 by h term out from this, I'm going to and basically into if I do this sort of thing, okay, that's what exactly we did it, right? Just be careful here, I think. Yeah, sorry for the confusion. It's quite straightforward. So basically, in this case, what we are trying to do is the blue color. Yeah, what we are trying to do is f is divided. Basically, this factor is divided here, and it comes here. That's why this is there. And then this was h, but this was w conjugate. So this conjugate goes to the other side, and that's why this h conjugate comes. So it's very simple expression. This is what we have, and what I'm going to take is this, I'm going to divide, I mean basically this particular factor from numerator and denominator by h, okay. So if I do that, h into h conjugate will become this guy, okay, square, and then this 1 by h will remain outside, and that's why this formula comes, and there is a reason why I put it in this, okay, this particular case. So this is fine. If you are working on Wiener filter, so finally you arrive at this particular expression, and I put it in this term because there is a 1 by h factor coming, and this ln, if you see this ln is nothing but your inversion, right? So that was you were doing earlier, and now there's an additional factor term which is coming, which is the beauty about Wiener filter, which is in this form, right? And here the only knowledge that you have is about h. You really don't know about f, for example, and n, for example, right? Noise and signal or the image is totally unknown to you. So that's where the beautiful thing comes. I think some of you might already know in what direction I am going, okay, and how beautiful this expression is, okay. And if you want to plug in your u and v back, the entire comprehensive equation looks like this, okay. Okay, so let's move on because the interesting part is here, okay. Just use this pointer is missing sometimes, yeah. So this is that beautiful expression, okay, and you can safely ignore u and v because that's just a coordinate. Always remember that this h is a matrix, okay, so that's reminds you all the time, u and v, okay. And then this factor is a symbol inverse filter, which you already know it, and this is your beautiful Wiener term that is coming into the picture. Now is the beauty. Okay, so we need to know the magnitude of f. That's a beautiful or the interesting aspect here. Okay, now if you observe carefully this particular equation, okay, so let me put it in simple term again for you too. Okay, so W is 1 by H, which is your inverse filter, okay, multiplied by this particular factor, okay, plus n by f square. Now what is this factor? So you don't know about f, you don't know about n, you only know about h. This, if you carefully observe, what is this? Noise by image. Okay, so this is already, you know what is it. Okay, I think it is there right there at your tip of your tongue. This is basically 1 by SNR, right? This is signal to noise, and you square it off, you have the signal to noise ratio square. Okay, so this is basically as simple as that. It is, so it's a constant you assume in the case of this, right? So it is basically something like you assume the ratio of your power spectrum of your signal to the power spectrum of your noise as a constant. It is an SNR, it's a scalar variable for you, and the entire Wiener filter coefficient became so beautifully represented in this very simple formula. I think sometimes I hate the putting U and V, so you can actually simple as that. It is 1 by H, which is your inverse filter, multiplied by a factor which is basically H square by H square plus 1 by SNR. Okay, some people even ignore this and put a factor K. Okay, so simple as that. So no knowledge of your image is required, no knowledge of the noise in the system is required. You just vary that parameter, hyperparameter K. You already know the transfer function approximately H. Okay, so that the derivation or the identification of the transfer function is very important. Okay, so don't ignore that. So this can be done experimentally as we discussed, or it can be done even from the image itself. Locally you find a region where you feel like impulse response is possible, and that's it. Okay. Okay, so let me just discard all the ink here. So this is a classic illustration of the same problem that we discussed when we discussed about the inverse filter. Okay, so same thing. So you have the image here. Let me again zoom into this region. Yeah. So you have the signal or image spectrum here corrupted by a degrading function, which is obviously this black one, added with noise, which looks like this. And then in the inverse filter was something like this, and a representation of the Wiener filter, if you go by the derivation and finally put those numbers in, it looks like this, and then if you do, you may get something like this. Okay, so that is the estimate, which is much better than the inverse filter, right? So you can see the difference. It's not really perfect, and going to f of uv perfectly is almost impossible, but we will try to go as close to that, and Wiener filter will help you to go as close to the original image. In what sense? In minimum square error sense. Okay, so if you do Wiener filter, if you use this kernel, then what you achieve is the error between f hat, which is your estimate, the spectrum of your estimated or restored image, minus your original, this will be minimum, right? So this is what you are ensuring by using this particular expression. So we will see that during the hands-on. I will show you some examples of Wiener filter, but let's actually discuss some examples from the textbook. Okay, so from the Gonzalez book. So this is a satellite map which was corrupted. Okay, so the blurred, if you use a direct inversion, this is the result looks like, and this is what I was telling you. If there is some noise in the signal, you're going to really get having a lot of issues, and this really is bad. And if you use Wiener filter, you can see how the original image looks like. Okay, so if you see the textbook, you can see the blurred image also. I didn't show you that here. Okay, so this is an example, and then another example. So this is a motion blur plus some noise. Okay, so this particular column is actually I mean this expression, let me put this way, f of xy convolved with, okay, sorry, sorry for that. So f of xy convolved with h of xy plus eta of xy, right? So this entire column is a combination of that. This is the noise which is actually very high here, slightly an order of magnitude less here, 5 times less here. So this is really no noisy image, it only has the blurring. So in this case, this guy, the degrading function is a motion, okay? So this is yeah. So in this case there is heavy noise plus motion. In this case slightly less noise plus same motion. In this case mostly only motion. There is no noise in this case. So these results are the results if I do a simple inverse filter. So I know the estimate of h of xy. So I am going to use that. If I just do an inverse operation, basically I take the Fourier spectrum, okay, so G, and I do 1 by h multiplication. If I do that, I get this, this and this for the 3 noise cases. So you can see here it is much better because the noise is not that significant, and you are able to recover sort of what is the image looking like, right? And these are the results for the Wiener filter, and you can see that this is okay compared to this, nothing is there here. This is much better, and you see this, okay, this is very beautiful, right? So that is the power of Wiener filter. So I hope I am not confusing you in any terms. So let me again, I mean, this is a good opportunity to really go back and discuss on that. So our model is something like you have the signal coming f of x comma y. So this is a very important model which is heavily used. It is passed through a degrading function, right? So this is a degrading function. Let's assume it to be h of xy. Okay, so every pixel is getting degraded, and then you add some addition of noise, eta of xy, and then what you have is g of xy. So this is your observed image, right? Your observed image is g of xy. So now I take the observed image, you are going to do digital image processing. You take a g of xy, which is your corrupted inferior image, you pass it through a filter, okay, and you get something like f hat of xy. So let me put this as h hat of xy is a filter coefficient, okay, and when h hat of xy, okay, is Wiener filter, then you can guarantee that the error between f of xy and your this one, right, this error, mean square error, is going to be minimum, okay. So that is the beauty about Wiener filter. I hope there is no confusion here. If there is confusion, we will clear that during the hands-on session, okay. So with that we sort of covered the entire lecture for this week, okay, only 2 short lectures, but I want to show some more insights onto you. So we talked about the mean square error, right? We talked about the mean square error between f of xy and your desired image in many of the times, right? So this square error. So are there better measurements than this? Yes, there are many. So one of them is SSIM, okay. So this is structural similarity index, okay. So this is actually something which we will discuss when we maybe discuss about the convolutional neural networks part. So we only discussed about one filter which can actually minimize the error between the restored signal and the possibly the original ground truth, right, and that is the Wiener filter, okay. So we will discuss about other options as we go along, because otherwise it will be boring for you if I introduce all sorts of measures. So Wiener filter is a filter which is optimum in the mean square error sense, okay. So that's it from me for this week, and see you in the hands-on for next week, okay. Thank you, bye.